Hi everyone, welcome to a new tutorial about pixel shaders in Max and visual music. I just have a brief announcement before we begin. I just created a Patreon page where you can support my work. This is an ongoing effort for me to create content that can be helpful to other audiovisual artists and people that are interested in general. So you can go ahead and click on the link below to support me and my work. Of course, having some positive feedback and financial support is very important, as I'm dedicating a lot of time to this work, and I'm happy to do it. But it's always nice to have to feel that somebody is interested and can support more of this content to be output. So please check it out and let's give it a go. What I'm trying to do in this video is to demystify the idea of ray marching that can be sometimes it can seem a little counterintuitive or complex, and try to explain it in a way that it's easy to understand and hopefully easy to implement as well. Ray marching is a technique that it's used to create three-dimensional shapes. I'm going to talk about this in the context of Max and Jitter. This is not commonly used in Max and Jitter as far as I know. It's an option that we should know whenever we do visuals in Max, because sometimes it offers possibilities that OpenGL does not. And also it can be efficient in a way that it relies on the GPU entirely, leaving the CPU alone so that we can do audio stuff with it. So what is ray marching? Ray marching is done entirely in the fragment shader. So we don't deal with vertices and the classic OpenGL pipeline. What it's usually called rasterization, meaning like translation of a vertex information into a virtual three-dimensional space. So we skip that entirely. We skip entirely the rasterization process, and we go directly into the fragment shader. So we need a way of translating the pixel coordinates, which is all we have pretty much in a fragment shader, into information that can be used to render a 3D shape. This is possible. It's implemented through the technique of ray marching. One of the problems when learning ray marching, as far as I'm concerned at least, is that the nomenclature for the functions that are used is not standardized. Whenever we look at shaders that use ray marching, the names of the functions might not always be the same. The way that ray marching is implemented in detail can vary also. Why do we need to learn ray marching? We don't need to, but if we want to learn how to make those nice shaders that you can find on ShaderToy, it's good to know how it works, and it's good to understand how we can use it, how we can change it, how we can tweak the different techniques to better fit our goals. The most important thing I would say to understand ray marching is to understand the sine distance functions. So what a sine distance function does is it returns the length of this vector. The vector goes from my origin to the surface, in this case a circle. In order for the sine distance function to work, I need to have two vectors. One is my origin, another one is the direction. In this case, the vector origin is 0, 0, and the distance between the ray origin and the point at which the ray direction hits the surface is the return value of my SDF. And it's assigned this function because the value will be positive here and negative once I pass the the shape that I'm trying to trace. So in order for the ray marching to work, I need these SDF functions that usually are contained in a container function, usually called either map or scene. As I mentioned, these names can vary based on who made the shader, but you will find some variations of these function where you will find all of the objects, all of the SDFs contained. So the other function that I will find is the ray marching function, and that's usually called either ray marching or intersect scene, something like that. The loop that implements ray marching will call the SDF container function multiple times in order to get closer and closer to the surface. The ray marching function returns also a floating point value, which is the distance between the point, my ray origin, as I mentioned, and the point on the surface based on the ray direction. Let's see how this is implemented within the max and jitter context. So this is pretty much all we need, all of the objects we need to do a ray marching scene in jitter in max. Everything is going to be done into the JxS lab that contains a file, a JxS file. I should save this file in the same directory where my patch is. This is always the case when we do this kind of work. Let's call it ray march JxS. So it's important to keep the JxS extension to the file for JxS lab to load it properly. And then I can give JxS lab the attribute app file. So I can just go down where it says start shader toy paste and just use this as my space where I'm going to do my programming. So what I like to do is, first of all, get rid of the indentation. We don't need it. It doesn't affect the result. So, and I like to keep curly brackets like that, but that's up to you. And the first thing we need to do is to transform the fragment coordinates. The frag coord, which is the pixel coordinate of the shader, into a Sine normalized coordinate space, which means I want the pixels to be indexed from -1 to 1 in both direction, in both dimension. So the x and the y dimension. 2 floating point times frag coord minus I resolution xy, and this will give me coordinates that go from minus the resolution to plus the resolution. So it's like it's double the size and it's signed. So what I need to do is to divide it by the resolution, but since I want to preserve the ratio of the screen, I can just divide it by the resolution by the I resolution y. So now my coordinates are from -1 to 1. So now that I have normalized my coordinates, I can get rid of this. I can keep the output to screen line, and I can start implementing my ray marching by first of all creating my SDF for the sphere. I will use the map function as the SDF container function, even though in this case it's going to be just one SDF, and this might be overkill. Sphere is simply the length of my point in 3D space minus the radius of the sphere. So the length minus the radius if the sphere is placed at vector 0, 0, 0. If I wanted my sphere to be at a different position than 0, 0, 0, then I would just translate the space to that point by subtracting my position from the point that I'm tracing the sphere from. In this case, I'm going to leave my sphere at 0, 0, 0, and then I will return the sphere. So this is my map function, my mapping function, where my actual object is. And I need to call this function within a ray marching loop. So this will also return a float, just like the map function. But this function will contain the map function, and it will run it into a loop. Intersect is the name I choose, and differently from the map function, this the ray marching function takes array origin and letter vec3 ray direction. So I'm using the variable names usually found on in JLSL in Jitter, which is RO and RD. So I can start with a general with a distance of 0 as my starting point, and then I will accumulate this distance as I march through the scene. So I need to create a loop right away, and I can say if for int I equals 0, I less than max steps, and I plus plus, and then I will have my vec3, which is my p. It's equal to RO plus RD times the distance. So what I'm going to do is a step-by-step process where I start from my ray origin and march into the ray direction gradually, using the distance from my scene as my step. To calculate this step where I'm going through the scene, I can measure the distance of my P to the scene using the map function. And at this point, I have created my P, my point in space, and I can add my hit value to this value, so that next time I go through this loop, I will have increased my depth into the scene. And then I have my breakout condition, so that when I'm either too far into the scene, meaning I have not hit anything, or I have hit something and I'm close enough to get that value, then I can break out of this loop. So if the dist is more than a fixed value, max dist, or if the dist is less than a minimum value, which I can call surf dist, then I can break out of the loop. And the keyword for that is break. You can see at the bottom here that I have my language selected as GLSL, and GLSL recognizes break as a keyword, and it is color coded in purple, meaning that's a reserved word for breaking a loop. And so at this point, I can have my return, and my return is going to be my dist. I created a couple of, actually 3 different fixed values. And this can vary on the complexity of the scene, the precision that you want. But we can use a value such as 50, for instance. And this needs to be an integer value because I'm using an integer comparison here. Then I have my max dist, after which I'm not going to trace anything anymore. And finally, I have to define a the surf dist, which is this is going to be a small value. How close do I need to be to the scene in order to break out the condition? One thing that I made a mistake here, because you can see how p is a variable but radius isn't. So I can either do a float radius here, or I could do something like use this as also as a defined variable. And I like to have my defined variables distinct, and they're all capitalized. So at this point, I have the intersect done. I have my map done. And I have to implement this into my image. So how do I do that? So I need to, first of all, have vec3 ray origin. Let's say 0, 0, -2. So you might notice here I didn't put floating point values here, but since a vec3 is a floating point vector, as opposed to ivec3, which would be an integer vector, the floating point vector will assume that these are floating points. So in this case, I can get away with not putting the floating point. My ray direction is a bit more complex because for a ray direction, I need to have like a camera function that allows me to translate the vector into in a way that can be used in a 2-dimensional pixel coordinate system. I won't go into the details of how the camera function works. I'm just going to simply copy and paste it. For now, let's just assume that this function is a given, just like a max object. Again, just use it as it is. And you can see how it returns a matrix 3, a 3-dimensional matrix that allows me to rotate the ray origin, RO, and the target, the lookup point, which is in this case TA, and have also a camera tilt. So how I can rotate the camera according to if I need to. So let's create a lookup point, and that lookup point is where I'm looking at in the 3D space. Let's just look at the center of the space. We'll use the camera function to create a camera. Camera, and I have my ray origin, my lookup point, and a tilt, no tilt. We normalize the vector of the UV, adding the z dimension. Since this is a vector 2, the UV is a vector 2, and I need a vector 3 because now I'm entering a 3D space. So I'm adding the z and using my UV to get the redirection. I can call my intersect function. I'll call this hit, and my intersect RO, RD. Okay, once I get my hit value, so the distance from my ray origin to the scene in the ray direction, then I can use this value to start calculating my final output. And so we'll create a vec3 call, which will be my final output, and we'll set it to black. And then I will have a if condition where I take the hit value. If this is less than my max this, then I can do something. So the first thing I can do is just set it to white. Set the output to white. So I can do call equals vec3 1. And let's see what that does. So I save this. I go to max. So I get this. I get a sphere, but in this case, I can't really tell that it's a sphere because I see it in 2D. So in order to get something closer to a 3D representation of a sphere, I have to get a little more detail. So what I can do is to extract the normal. What is the surface like at that particular point on the sphere? And to do that, I need to use another function that I won't go into the detail of explaining, but just in general. The normal function is, it can be called also different things, can be called get normal. Usually the normal name will be init, so that's kind of easier to recognize. And you can see how I'm actually calling a map function also in this function. But in this case, I'm not calling it within a loop, so it's not as expensive as my ray marching function because I already know what the distance is. I'm gonna feed it a p-value, meaning a point in 3D space, so I don't have to march through the scene. I just want to know what the neighbors of this point are, so that I can calculate a derivative of the a derivative value at that point. I can use that function to do my light calculation, and that will be I can call this the norm. First of all, let me calculate the p value, and the p value, just like in the intersect function, is the ray origin plus the ray direction times the hit distance. That's already, I already have the hit value. So I just need to do this little line of code to get the P, and then I can get the normal, vec3, let's call it norm, and I can do normal and my P. I can use that to do my lighting. So before that, let's create a light position value, and let's normalize it to have just, again, just a directional vector. We don't need the magnitude for that. So normalize vec3, just give it a position, and then what the call will be, dot product of my light costs and the norm. This will give me the intensity of that light at that specific point. And since these values are from -1 to 1, I will normalize it from 0 to 1. So multiplying it by 0.5 and adding 0.5, now they're 0 to 1. And now I will have something different. Let me see. So I get an error, and I can go in my Max console and see what the error is. At line 77, I have a cast, implicit cast from float to vec3. And yes, because the dot product here is actually a floating point value. So I need to, what I can do is vec3 1. So multiply white, it can be any color, to this dot product and see if that works. And yes, and I have my sphere with my light calculated, and it's not, I can increase number of steps. Let me just shrink this window. If I increase the number of steps, you can see how the aliasing problems that I had at the edges are almost gone. I can decrease the surface distance. That doesn't do much. But there are ways of getting rid of the aliasing around. But for now, this is kind of beyond the scope of this tutorial. So there you go. This is a basic introductory um, video about ray marching. There are other ray marching videos on YouTube. This is original in that is implemented in Max, and while this particular output is not that exciting, Max and Jitter objects to control animation and to create shapes that react to music, for instance. And until the next time, stay tuned.